last time we talked about the Ising model, the ferromagnetic Ising model in one-dimensional system. And we first look at the t=0 situation where we know that there is a finite magnetization when this field is positive, where Si is +1 and Si becomes -1 when H is negative. But in order to get to this kind of non-trivial magnetization, we don't need to go to the thermodynamic limit. In other words, when we calculate this magnetization for the finite size Ising ferromagnet in 1D, the t=0 condition is sufficient to get the finite magnetization, because to minimize the free energy, as we mentioned last time, at any given finite size, average spin on any site I, take a finite value plus or minus 1 for this value of a magnetic field. This is exact at zero temperature, meaning we don't need to go to thermodynamic limit to see this, because if you minimize the free energy at 0 temperature for a finite size Ising ferromagnet, this is the ground state, period. So this is very special, and we will come back to this later. But this is very simple and obvious to see that at 0 temperature, this fully polarized spin on every site, either pointing up or down depending on the sign of the field, is a solution at ground state. And therefore, we indeed get a finite magnetization at 0 temperature, and there's a first order transition right at 0 field. Because when the field is actually infinitesimally larger than 0, you get +1 as magnetization and -1 magnetization when this field is actually slightly below 0. Okay? So right at this 0 field, you got a phase transition, but this phase transition is a first order jump, and we will get back to this later. But the main message is that, remember we mentioned many times that we need to go to thermodynamic limit in order to see the phase transition. But here, it seems that we don't need to go to thermodynamic limit to see this phase transition, because at t=0 in 1D, this Ising ferromagnet has a ground state of that configuration with a non-trivial magnetization. So we will come back to this later, but we don't just stop at 0 temperature. We need to go to finite temperature and to see whether a fully spin polarized Ising ferromagnetic ground state is stable against any finite temperature fluctuations or thermal fluctuations. In other words, we need to know whether there's a transition temperature, Tc, whether this is 0 or positive. Now we need to check this thermal fluctuation, the effect of the thermal fluctuations on the ground state at any given finite temperature. And to do so, we indeed need to consider the thermodynamic limit. In fact, we'll see in just a moment that in this one-dimensional Ising ferromagnet, order to disorder transition happening at exactly 0 temperature. Okay, so this is really surprising in some sense, but not unexpected in other sense. Okay, so let's just talk about this phase transition at any given finite temperature for a one-dimensional Ising ferromagnet. Okay, so we know that at t=0, the ground state is ordered with a finite magnetization at any given finite size. We are asked if this ordered state is stable against thermal fluctuations. Okay, so this is important. So if the thermal fluctuations, which will lead to this flip of the spins, and if that spin flips events get accumulated, then it's likely that this spin ordered state will be destroyed. But if these thermal fluctuations, which will flip the spin, just rarely happened, and then this the fully polarized ferromagnetic ground state can be stable. But which one will be realized? And we should analyze what the effect of the thermal fluctuations do on the fully polarized ferromagnetic ground state of the Ising model. So obviously, the thermal fluctuations are going to flip the spin. In other words, you may have a situation where you have a bunch of spin up spins on the left-hand side of the chain, but this is the ground state. But you may have another different situation where all the spins are pointing down, and it will create a so-called domain wall, which separates the spin up sides from the spin down sides. And this is actually the low energy excitations. remember that at t equals 0, you may have all spin polarized in the zero field limit. Either all the spins are point up or point down, so that's all equivalent. But remember, when you have thermal fluctuations at finite temperature, this will lead to the spin flip. And where is the spin flip? In this case, just right next to the domain wall, you get a spin flip, remember. In other words, for these two spins that are anti-parallel to each other, encircled by the yellow, so they are caused by the thermal fluctuations which make them anti-parallel, or make all the spin on the left-hand side anti-parallel to the spin on the right-hand side. But either left or right-hand side of the domain wall, you get all spins parallel, so which satisfy this Ising term over here. And in the limit of the infinitesimal amount of field, say when the field is positive, then this will favor this all spin up, and then this all spin down stays, even though it is satisfied by this J term, but it may break this minimization condition for this Zeeman term, H term. But when this H goes to 0, we don't care about this Zeeman term, but we just care about how many such spin flip terms that is created by generating domain wall. So this domain wall is going to create spin flip configurations which will increase the free energy of the system. And let's try to evaluate the energy of such domain wall configurations compared to the spin polarized, all spins up, ground state at 0 temperature. So this is ground state at t equals 0. So meaning we want to ask which energy is lower, and what is the difference between the states with one domain wall compared to the no domain wall, ground state. Okay, what is the energy difference? And of course, we expect that this, with a single domain wall, the total energy of that configuration should be slightly higher than the ground state at finite temperature. So what we like to count or calculate is the number of spin flips. So we would like to estimate the number of spin flip. And we would like to calculate the percentage of the number of spin flips compared to the total number of spin. And there are two situations, whether this percentage of the spin flip is small or large. So how small can that be? Well, it depends on how many spin flips events are there. Suppose there are only a small percentage of the spins get flipped by putting the domain wall. And you could just take a limit, the thermodynamic limit, to calculate the total number of spin flip and subtract from the total number of spins. Suppose there are only a small percentage of the spins that are flipped, and this number is called the little n here. This is the number of spin flips, and this number is much less than the total number of spins on your lattice. Then this number in the numerator is actually almost the same as the total number of spins in the denominator, and therefore this ratio is actually almost 1, but slightly below 1, so say 98%. And that kind of value is what we call when we have a small number of spin flips. And in this case, if we have just a small percentage of spin got flipped, then we are safe. Then the ground state is actually stable. Because when we take the thermodynamic limit, when n goes to infinity, then this limit is actually almost 1, or exactly 1 when n is exactly at infinity. But there's another situation which is the opposite case, where we have a very large percentage of spin flip, and we would like to take the same limit, but this time, this is much less than 1. Namely, when this little n, the number of spin flips, is comparable to the total number of spins, then the numerator is actually almost 0. And compared to the denominator, which is almost infinity, and as a result, when we take the thermodynamic limit, if the little n is of the same order of magnitude as the capital N of omega, then the ratio is really, really tiny. Meaning we have a large percentage of spin flips, and so all the stable configuration of a ferromagnetic ground state is actually suppressed. So we get disordered phase. That's the importance of estimating the number of spin flips. at finite temperature. And creating the domain wall is the cheapest way that you introduce the thermal fluctuations, and this is the effect on the ground state of Ising ferromagnet at 0 temperature. So then we have a criterion to tell whether this kind of a domain wall formation is going to suppress the ground state or not suppress the ground state of a fully polarized Ising model. Then we could try to estimate the free energy of Ising ferro at T positive and with domain wall. And first we consider just a single domain wall at very low temperature. And to calculate the total free energy of a system at finite temperature, we need to, again, calculate the partition function at the finite size and finite temperature. And then we take the thermodynamic limits and see for a single domain wall, energy actually is lowered, and by how much amount. And we could easily calculate this and define the free energy. From your statistical mechanics knowledge, you know that the free energy is given by the difference between this internal energy and T times this entropy S. Then there are two free energies at finite temperatures. One is the fully polarized spin at finite temperature. Another is the single domain wall configurations at finite temperature. And we'd like to compare the free energy of the two, right? So let's just compute the free energy of a single domain wall, and I will call the free energy of a fully polarized spin this F++, meaning all the spins are pointing up, and I call this free energy F++. And of course, with a single spin flip near this domain wall, I have the free energy, I call this F plus minus. And the reason why I call this, I denote this free energy by F plus minus is because there is a bad bond, okay, anti-parallel spins right next to this domain wall. And so I call this plus and minus because one spin is plus, another one is minus. And I want to compare these two free energies, and therefore I could just calculate the difference of the free energy, and I define this difference delta Fn, which is the F plus minus minus F plus plus. Okay, so then I could calculate separately total internal energy of the plus plus configurations and then plus minus configurations, and also I should estimate the entropy in these two cases, and then I could just evaluate the total difference. So what are the E plus plus and E plus minus equal to? So the E plus plus is the total internal energy of all spin polarized states at any given finite temperature. This is minus Nj in the limit of the zero field, right? Because when all the spins point up and the free energy coming from this Hamiltonian and just contributed from this minus J term when all the spins are up, and you get N bonds, right? And therefore you get minus N times J. But what about this E plus minus? Well, you get all spin parallel to the left of this yellow circle and also to the right of this yellow circle, but you get one bad bond right here. So this is what we call this bad bond, because between these two anti-parallel spins, it is not satisfying the parallel condition written there for the Ising ferromagnet. Okay, so we call this bad bond, but there's just one single bad bond. So all the other n-1 bonds are all good bonds, so they should carry this minus bracket n-1 times J, this internal energy. But I got this one bad bond will lead to this positive J of this internal energy, because if I plug in this bad bond configurations, one spin up, the other spin down, back to this Ising exchange coupling term, you got spin up here on side I and spin down on side J, and so plus 1 times minus 1 is actually minus 1. Minus 1 times minus 1 is actually plus 1. So that's how you get this plus 1. Okay? So now I simply just sum up these two terms. I get minus Nj plus 2J. And therefore, when I plug in the energy difference of the internal energy parts for these two configurations, I get what? 2J, so E plus minus minus E plus plus minus T times delta, the difference in entropy. Okay, so the difference in internal energy is actually what? 2 times J, right? Because this is minus Nj and this is also minus Nj, so you cancel that when you take the difference, but the remaining piece of this energy difference is actually 2J precisely. Therefore, this is given by 2J minus T times delta Sn. This is not done yet. We still need to estimate the entropy difference between these two configurations at any finite temperature, and we should calculate how many types configurations of the single domain wall can be generated for a one-dimensional Ising Ferromagnet. Okay, so I've used up my space of the blackboard, so let's take a short break, and when we come back, we'll continue finishing up these calculations and estimations. So just before the break, we estimated the free energy difference between the fully polarized ground state and configuration with single domain wall, where single domain wall will lead to the single spin flip right next to this domain wall. And other spins are either pointing up or parallel to each other on the neighboring sides, or pointing down or parallel and relative to the neighbors. So the remaining job is to estimate this entropy difference between these two configurations. And in this very naive, very simple configuration, it's all spin pointing up, and the entropy is actually 0 because all spins already pointing up. There's no other configurations. But then configurations with the one domain wall, we have n degrees of freedom because remember the entropy is given by kBT times log, but what inside the log is the value which tells us all possible configurations of that state, and we know that this position of the domain wall can be anywhere along the chain. It does not necessarily to be in that location as I plotted here. It could be anywhere. It could be between the first and second spins. It could be between the last two spins. It could be anywhere along the chain, right? So how many possible configurations to put this domain wall, and we need to calculate that. But this is easy because there are n spins, so there must be n possible ways to insert the single domain wall, and it could be here, 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 until the very last. So there are n possible ways to insert that single domain wall along the chain. Consequently, the entropy associated with that state with the single domain wall carry kBT times log n. So the total difference in free energy between these two states can be accurately estimated as 2J minus kBT times log n. But then we should ask whether this free energy difference is positive or negative. Okay, so let me summarize the possible results. So if delta F is actually positive, meaning the remember the delta F is defined as F plus minus subtract from this F plus plus. So if delta F is actually positive, meaning this total free energy corresponding to this plus plus is actually lower than that for plus minus, in that case the all plus plus is actually stable, because statistically from your thermodynamic statistical mechanics, you know that the ground state or the favored phase, the stable phase, is actually the state with lower free energy. Okay, so if this F plus plus is lower than the F plus minus, then the F plus plus wins. It should be stable state. But if on the other hand it is the F plus minus which wins, which means that this gives the negative value for this delta Fn, and in that case the system will favor to form a single domain wall, and this will be stable. But which one wins? Let's just look at this formula one more time. Okay, so you see there are two terms. One is positive 2J, another is negative value is minus kBT times log n, but this n is number of sites or number of spins, and we haven't taken thermodynamic limit yet, but everything is is in terms of the finite size, but we should take the thermodynamic limit. When we take a thermodynamic limit, meaning when the system size goes to infinity or the number of particles goes to infinity. So what happens then? Of course, when n goes to infinity, the log n also goes to infinity, and you get minus infinity and also two finite positive value to be added, okay? And if that is the case, then it is certainly true that this delta f is going to be minus infinity. All right, so that's really the simple analysis, simple mathematics, that when n goes to infinity, this difference in free energy between these two states is minus infinity, which means that this is negative value, which means that it is always favorable to create a domain wall. In other words, at any given finite temperature, but in the thermodynamic limit, the probability of creating a domain wall, a single domain wall, is what? Is actually close to 1. It's actually 1. Because the free energy difference is actually minus infinity, and remember, the probability of having a configuration is actually based on this partition function, is 1 over z times e to the minus beta fn. And if you really calculate this Boltzmann weight, and this is what? Delta fn is actually minus infinity, and therefore this Boltzmann weight is actually almost infinity, but you know that there should be the same amount of result hidden in this partition function, so you get a full cancellation between the denominator and the numerator, and therefore this probability of finding the system at finite temperature to have a single domain wall is almost 100%, right? So it is always the case that when you have any finite temperature, and this system always wants to create a single domain wall in the thermodynamic limit. So this is the important lesson that we learned from this simple estimation. So in other words, at any given temperature, the system is unstable against a single domain wall to be formed. And therefore, the true lower energy state, or the system, will favor the single domain wall, that kind of configuration, and any given finite temperature based on this analysis. So a fully polarized state is no longer a stable state. But is the single domain wall configuration a stable state? No, certainly not. Okay, so you can imagine that the single domain wall is still unstable against a configuration with two domain walls to be formed. Because based on the same argument, so I could imagine that I insert one more domain wall right here. I could just flip the spins on the right part of this second domain wall like this, so that I could have two bed bonds, right? For the two domain wall configuration, and I could easily calculate this free energy difference between this two domain wall and single domain wall. And I, based on the same results, that in the thermodynamic limit, the systems always favor to have domain wall, and so the system will not stop at just a single domain wall, so it will create two domain walls to lower the energy even further, because a single domain wall will lead to the lower the free energy by creating another minus kBT times log n, that amount of the entropy gain. So the system would like to maximize the entropy and to lower the free energy, all right? So you could use this argument to say that, well, the system will create more domain walls, like 3 domain walls and 4 domain walls. So it will not stop at any finite number of domain walls. So 3 domain walls and 4 domain wall and 5 domain wall. So you will create at the end infinite number of domain wall, but you don't have infinite number of spins. But if you have n spins at maximum, you have n domain walls. Therefore, the more domain walls you create, the lower the energy. So the system is favored to have as many domain walls as possible. In that case, so you may consider that between all the spins, there's domain wall. This is that, and so on and so forth. As a result, if you sum over all the spin configuration, the spin moment around all the sides to be summed over, and you get equal number of spin up and equal number of spin down state, and you get 0 at any given finite temperature. All right, so that's the solution. So for Ising ferromagnet, at any given finite temperature, the thermal fluctuations will lead to the domain walls to be formed, and the more domain walls to be formed, the lower the free energy will be. So the system would be favored to have infinite number of domain walls to be created. As a result, between just next to this domain wall, the two spins are anti-parallel to each other. As a result, you cancel all these upspin states and downspin states, so the net spin moment is actually 0. So we get a very important conclusion here. So for the Ising model, a ferromagnetic type at 0 temperature, you get ordered phase. But once you just turn on this temperature, just small amounts, infinitesimal amount of temperature is going to suppress this long-range order, and the system will become disordered. So the disordered state is a stable state at any finite temperature. So this is very crucial that this argument is valid for any arbitrary finite temperature. Even infinitesimal amount of temperature is sufficient to kill this Ising ferromagnetic state at 0 temperature, which means that we have a transition. Suppose this is the axis of temperature and this is the 0 temperature, and we know that fully polarized Ising ground state occurs at t equals 0 as a ground state. But any finite temperature, the system is going to be disordered. So which means that the spins will be disordered, and the average spin moment is actually 0. All right, so you got the phase transition at t equals 0. So the phase transition occur exactly at t equals 0. Means that our Tc, the critical temperature here, is at 0 temperature. So that is really special case for Ising ferromagnet in 1D. Let's take a short break and we'll come back. So let me summarize our conclusion for a one-dimensional Ising ferromagnet. And as we know that as you turn on the temperature, even just slightly in one dimension, this Ising ferromagnet is actually unstable. The ground state of fully polarized configuration is unstable against the creation of domain walls. And then it will kill your ferromagnetic order at any given finite temperature in the thermodynamic limit. And a similar situation is also applied to the Ising antiferromagnet, where at the ground state, all the spins on neighboring sides are anti-parallel to each other. Remember, this J term is actually plus J, and for the Ising ferromagnet, the J terms in the Hamiltonian is actually minus J, where J is positive value. So how to create a domain wall if we are dealing with Ising antiferromagnet? Well, the creation of domain wall is very much similar to the Ising ferromagnetic case, but here we need to group these two spins together, and these configurations of this red group of two anti-parallel spins alternate. So this is up-down, but next to the domain wall, these two spins configurations changes to down-up, then up-down, then down-up, and so on and so forth. So-called staggered magnetization, which is the difference between this sublattice A and B for this magnetization, is actually changes sign. Okay, so on average, you don't have any order at all. So this is the way that the system disordered for Ising antiferromagnet in 1D. So the conclusion is the same. As I mentioned, from the time reversal symmetry point of view, all the properties for the Ising ferromagnet should apply to the Ising antiferromagnet because of this time reversal symmetry of the Hamiltonian of the two systems. So another important remark I would like to make is that this kind of a conclusion that the spin flips at finite temperature will suppress the long-range order for Ising model. Remember, in the Ising model, the spins coupled to the other spins only is nearest neighbor sides. So it's a nearest neighbor interaction, and it is typical, the simplest example of a so-called short-range interaction. But if we consider the ferromagnets, not Ising type, but with a long-range interaction, meaning the spins on side I will interact spin on side J over a couple of finite lattice constants, just go beyond the single lattice distance, and they are still interact with each other. So in that case, we call this a long-range interaction. So for a ferromagnet in 1D with a long-range interaction, where you could just imagine that Jij could decay just in the power law fashion with the exponent sigma, and we can show that we can calculate this again. The free energy difference between the fully polarized states and a single domain wall state when n goes to infinity is actually plus infinity when sigma is between 1 and 2. So in that case, for sigma, the long-range interaction with the exponent sigma between 1 and 2, in that case, this delta Fn is actually plus infinity, which indicates that, remember, that this fully polarized phase is actually stable against spin flips if delta Fn is positive. And here, this is plus infinity, indicating that this t equals 0 spin polarized state is a stable state at a finite temperature, which means that Tc is no longer at 0 temperature for a long-range spin-spin interacting ferromagnet. So in particular, if sigma is less than 1, then this n goes to infinity limit does not exist anymore. But if sigma is larger than 2, then we have a short-range spin order, which means that the spins may form some finite-sized clusters. Within the cluster, they obey some sort of a ferromagnetic or antiferromagnetic type of configuration, but beyond that cluster, there's no correlation between the spins. It's called short-range order. So exactly at sigma equals to 2, which is 1 over r squared, kind of a long-range spin interaction, then you can calculate delta En and delta Sn, and you can sum up these two terms, and you get delta Fm. In that case, you get log n times j minus kBt, which means that when kBt is actually greater than that value, j, then the system is disordered. On the other hand, if temperature is below that amount of critical value, then the order is stable. Okay, so there is an order to disorder transition at final temperature, and the critical temperature when sigma is 2 is actually right at this value of j. So this is a remark concerning the conclusion we made for the Ising model. But the Ising model is just a special case in the spin system. So in reality, the spins can interact with the long-distance partner far away from the side I, but in practice, they most likely will interact with the nearest neighbor spins. So the Ising model really describes a class of materials, but not all the magnetic materials. Okay? And that's why we need to be careful that don't want to get confused by the conclusion from this Ising model and from this long-range interacting spin models. Okay, so we may get back to this point later, but let's just go to the two-dimensional limit, and we want to analyze again this free energy difference between this fully polarized state and the domain wall states. So let's just consider the Ising ferromagnet at finite temperature, but when we have two-dimensional lattice. So the simplest lattice in 2D is the square lattice, like this. And we may have some spins on the lattice pointing up, but we may have some other spins on the lattice which point down, and they are separated from each other by, again, a domain wall. So now the domain wall is actually a two-dimensional geometry. Okay, suppose that I have two-dimensional Ising ferromagnet on the square lattice, and at any given finite temperature, we know that thermal fluctuations are going to generate some domain wall, but what can the domain wall look like? Well, this is certainly one example of what domain wall may look like. So you can simply just encircle the region where all the spins are point up or point down, and then the other side of this area belong to the other spin configuration, and then you have bed bonds. They are simply just located right at the boundary, right? So right here, and 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 so on and so forth. So then what we could just use a cartoon picture to illustrate this kind of domain boundary in 2D system. So where all the spin up stays actually inside this box, and all the spins outside of the box are pointing in the other direction. And you may have n number of bed bounds if you have such a configuration, but you could have some very rough estimation of how many domain wall could be generated. Well, a very crude, rough estimation is that the number of domain wall is about this number, so-called number of neighbors, the coordination number, z to the power of n. So where z is number of neighbors. In 2D, z is actually 4. There are 4. And n is actually a number of bed bounds. So that's just a very crude approximation or estimation, but this is overestimate. This is the overestimated value because we like to avoid self-crossing. So we should more accurately calculate this number of nearest neighbor and the number of possible domain walls. So suppose this is, again, the square lattice, and I have 4 directions to go. If I have a bed bound at this boundary, suppose this is one of the bed bounds that I would like to cross, but once I go into that bed bound, I have 3 choices, right? Not 4. I have only 3 choices. So each step to form a domain wall, going through this by following this bed bound directions, we are able to just get this domain wall. Remember, this is also a bed bound. But at each intersection, crossroad, when we cross a bed bound, we have 3 choices: going up, going to the right, or going downwards. Okay? So each step goes in z minus 1 directions. So they're not z direction, but z subtract from 1, because I should self-avoid crossing myself. And therefore, this entropy difference between the fully polarized and a 2-dimensional domain wall is actually what? kbt log z minus 1 to the power of n, where n is actually the number of spins. Okay? So the number of possible bounds, equivalently. So then we could just sum up all these contributions of total free energy. Delta of n is actually 2 times j times n minus m times kbt log z minus 1. And 2 times j subtract from kbt log z minus 1, and everything multiplied by capital N. So then we could just estimate whether there's a finite temperature phase transition. So delta Fn goes to minus infinity when temperature is actually greater than this critical temperature. And the critical temperature is actually 2j times kb log z minus 1. Okay, so this becomes very clear that we have a finite temperature phase transition, and you could very easily see that if this 2j is larger than this log term, then delta Fn is actually positive. If 2j is less than that, kbt log z minus 1, and it is negative. And when delta Fn becomes negative, which means that when temperature is greater than that amount, which we can define as the critical temperature, then the state becomes disordered. But delta Fn, suppose, is actually positive, which is true, and the system is still ordered. So then we could just draw a phase diagram in terms of the temperature at zero field for Ising Ferromagnet in 2D. So for temperature below Tc, you get magnetization non-zero. Remember that. It's ordered phase. But for T above Tc, you get disordered phase. And Tc is about that amount, but remember this amount is also some kind of estimation or approximation. So this value is not exact. So the reason why this critical temperature is not exact is because even in that case, we self-avoid crossing the red arrow here, which improves the accuracy to estimate the entropy. This is still an overestimation. So this is still overestimation of entropy, because the boundary in this case is allowed to actually cross each other, because the boundary can cross each other. So we should not allow the boundary to cross each other. Therefore, we should impose further constraint to limit the choices we have, not just from the simple naive 3 remaining directions, but the boundary cannot cross each other. So, for example, I cannot have such a domain wall, because in that case, this boundary is actually cross each other. But then I cannot rule out such a boundary crossing when I simply just estimate the amount of entropy by this kind of approach. So we should further suppress such a possibility for boundary crossing, okay? But that requires further more rigorous estimation. And we are here just for a rough estimation. And the exact value of this Tc over J is about 2.27. This is the exact critical temperature. But here, approximated value is about 1.8. So this is 4 minus 1 is actually 3. So log 3 times Kb and divided by 2. So that concludes more or less this Ising model in 2D. Okay, so we just follow the similar approach that we did for the one-dimensional Ising model by creating a domain wall for the 2D case, but in the 2D case, the domain wall forms the two-dimensional area. Then we need to be careful to estimate the number of ways to get this domain wall, and a simple estimation tells us that this will lead to the finite temperature phase transition, and this Tc is about that much. For a 2D Ising model, the ferromagnetic case, we indeed have a finite temperature phase transition, unlike the one-dimensional case where we don't have ordered phase at any given finite temperature, but in 2D we have. And the underlying reason why we have the long-range ordered finite temperature in two-dimensional Ising model, but we don't have that in 1D, is that we have more neighbors in 2D compared to 1D. For example, if you have a spin flip in a two-dimensional case like this, so let me just use this shaded area. For example, for a single spin right here, apart from the spin flip site above that particular site at I, all the other 3 spins, say right here and there, are all good bounds. So we have 3 good bounds, but only just 1 bad bound. So the percentage of this bad bound to the good bound, or total number of bounds, is actually 25, right? So you got 1 bad bound out of the 4 bounds. So in other words, if there are just 1 bad bound, just would like to flip the spin on the side I, but there are 3 neighbors of this spin on side I who will actually hold that parallel configuration for them. However, for a one-dimensional case, if you have spin up on the side I, but you get bad bound on the right side of the spin on side I, so I get bad bound here. And I have spin up on side I minus 1. So now you can calculate the percentage of your spin flip relative to the full polarized configuration. You find that this percentage is really high, meaning you have a 1 bad bound, but total number of bounds is actually 2. So you got 50% of bad bounds. So the damage caused by the bad bounds is actually much more serious in 1D than in 2D, because in 2D you get only 25% of bad bound, but in 1D it is 50%. All right? So in other words, this is a very naive hand-waving argument, but this kind of provides us with a good physical insight and intuition to explain why the Ising Ferromagnet in 2D favors the finite temperature ordered state, but it is disfavor the ordered state for a one-dimensional ferromagnet. So let's take a short break. When we come back, we will discuss the finite size effect and impossibility of a phase transition at any given finite size. Let's continue. We now look at the phase transition from a different perspective. Namely, we would like to keep everything at finite temperature, and we don't know whether the system is ordered or not at any finite temperature. We like to calculate the magnetization at a finite size and at a finite temperature. But if we do so, then we have a problem here, because I mentioned earlier that the free energy density should obey certain analytical properties. And it also has a symmetry, for example, in the Ising model, between the field along the plus or minus z direction, because the symmetry of the Hamiltonian partition function leads to symmetry between plus and minus the field. As a result, if you calculate this magnetization for an Ising model under the field at any given finite size, and you could just very easily just calculate this magnetization from these two different forms of the free energy, but they are all equivalent. So you could just come from the first on the left-hand side of the equation, and you calculate the magnetization. And this is a minus of partial free energy derivative partial h. But then you can use this identity actually to rewrite this derivative in terms of the minus h. And you get the minus times this n omega times m omega at minus h. So, but then these two derivatives should match, because you get this kind of identity, okay, from this symmetry of the free energy, okay. But this tells us that this magnetization is actually equal to the minus of the magnetization when this h goes to zero limits. But what does it mean? Well, this immediately tells us that magnetization at any given finite size in the limit of h goes zero is actually zero. So you don't get any magnetization, and this is true all the way to temperature goes zero. So in other words, if we come from finite temperature and finite size, and you'll get the wrong conclusion. But we know that this magnetization, when h equals zero and temperature equals zero, is non-zero. It's actually plus minus 1. Remember that. So this is correct, and this is wrong. But again, the question is, what's wrong? So where does it go wrong? So this is an important point of this title, that it is not possible to have any phase transition at finite temperature at any given finite size. So that is intimately related to the order of taking limits. So we need to take thermodynamic limits first, meaning before taking other couplings to limiting values, say before taking the field to zero, we should take the volume of the system to infinity first, or number of particles of the system goes to infinity before we take any other limits. So because these two operations give you two different results. So on the left-hand side of this calculation, I keep the system size at a finite value always, which means that I take this field goes to zero limit first by keeping the finite size of the system, and then afterwards I take the size to infinity. But this is the wrong order, because we should take the thermodynamic limit first. This is the correct order to take these two limits, meaning we need to take n goes to infinity limit first. Then afterwards we can take any other limits later. In other words, the system needs to be in the thermodynamic limit first, and then you could see finite order parameters in that limit is reached. And therefore you get ordered phase. So if we take the wrong order of these two limits, then we don't get anything meaningful, because if we keep the system size finite first, then take this h goes zero first, then everything is zero, as I mentioned. So that goes back to the analytical properties of the free energy density as I defined a few lecture hours back. Remember that the free energy density should be continuous convex up function, but then in this case we need to be careful. So the free energy density as a function of the field is the free energy density by taking the thermodynamic limit first. Remember, we defined the thermodynamic limit by defining this free energy density, capital F at a finite size omega, divided by the total number of sites and omega, and taking the number of sites to infinity. And this is the proper definition of thermodynamic limits. So in principle, all this free energy density in this system with a phase transition should have well-behaved limits when you take this n goes to infinity. So now let's just look at the difference between the finite size behavior of this free energy density and the behavior of the free energy density at infinite size. So the blue curve represents the free energy at finite size, and the red curve corresponds to the free energy at infinite size. Remember the symmetry that I listed over there, that free energy density as a function of the field shows an even symmetry with respect to the field, but this property does not imply that magnetization should be zero. But this does imply the magnetization to be zero under only one condition, unless this free energy density as function of h is actually a smooth function in h. A smooth function in h means that if I take the limit on both sides of the field relative to zero field, I get the same results, which is zero. So if the free energy density is a smooth function of the field, then it implies that magnetization will be zero because of such a symmetry. And this is precisely what happened here in this plot, that the free energy density along the blue curve is actually a smooth function in h. And in that case, you automatically get zero magnetization in all cases. So, but you know that this is not correct result. So then this leads us to think that free energy density as a function of the field may not be a smooth function. Okay, in real case, the free energy density as a function of the field does not have to be a smooth function at all. It's like in this example here in the blue curve that we have a cusp right here, which is a sharp edge connecting these two parts of curve. It is continuous, but it is not smooth because you can take the limit of this differentiation on left side of the cusp and the right side of this cusp, and you don't get the same results. But still, this property satisfies this symmetry and all that analytical properties of free energy density. So which means that you get, for example, in this cusp shape, you do satisfy f of h is actually f of minus h. But if you calculate the derivative partial f partial h for h is actually 0 minus, it's actually not the same as partial f partial h when h is actually 0 plus. And the Ising model in the presence of field for 1D precisely belongs to this cusp situation. So in that case, we could just do Taylor expansion or just approximate this free energy density in terms of this cusp, which is the constant subjected by the absolute value of the field times the magnetization. So if I just use this form to actually model this cusp shape near this zero field, then I can get a good agreement with what we know for the Ising model at zero temperature in 1D. And the agreement is this. So if I calculate m plus, which is a slightly positive field, and actually 0 minus, and I get m plus, it's actually minus limit, h goes to 0 plus, partial f partial h, which is plus ms. I can calculate m minus, which is minus limit, h goes to 0 minus, partial f partial h, which is minus ms. So this is correct result based on what we know at zero temperature Ising model. So this tells us that in order to reproduce correctly the ground state of the ordered phase, at any finite temperature, we need to really calculate carefully. We need to actually take the thermodynamic limit first before taking these other couplings to zero. And the way that we take the thermodynamic limit first in this case is that we consider a thermodynamic limit of that free energy density. So in other words, we don't consider a smooth free energy density at finite temperature to begin with. We should take the red cusp function at the beginning of our calculation. Okay? Meaning we need to take the thermodynamic limit first. But you may ask, why does this free energy density looks like a cusp Ising model? We will discuss that next time. Okay, so we will come back to this point next time to really get this picture right, that the free energy density for Ising model as function of field in the thermodynamic limit does look like a cusp rather than a smooth function like this. So that concludes our lectures today. So I'll see you next time.